systems of linear inequalities. So that's what this is all about. And that will close out our chapter 6. So we're going to look at 6.5. It's all about solving systems of linear inequalities, and the technique we're going to use is just graphing. So using graphing. Okay, let me show you what a system might be. Here's an example. Now it's in equations, we're dealing with inequalities. So maybe I have x minus y is less than or equal to 3. And maybe I have 2x plus y is greater than negative 1. So I have these two inequalities. Well, let's graph each inequality. And maybe I'll make this one in blue and the other one in red. So when I go here, I go right to graphing. I go to my Cartesian coordinate system. And let's put some things in over here so I get okay, so let's graph each of those equations. Let's say I'm going to graph this one in blue. So I can do the intercepts if I wanted to. I'm going to graph the equality right now. So I'm going to have over here, let's see, y is, when x is 0, y is negative 3, so I'm down here. I could just put a couple of points in if I wanted to. So I get 0, comma, negative 3. When y is 0, x is over here at positive 3. Okay, so those 2 points are on my line. Now, since this is equal to, I'm going to graph that with a solid line. Okay, so I graph it over here, try and get it as close as possible, and that's what it looks like. And then you can pick a test point. Now, this is an inequality. That's at the boundary of it. Now, I'm either going to shade above or beneath it, one or the other. Typically, what you can do is pick a test point. So I might pick the origin as a test point, as my test point. An easy point. And I put it into the inequality. And if it gives me a true statement, then the solution is on that side of the line. So 0 minus 0 is 0, and 0 is less than or equal to 3. So in that case, the test point works. So I shade everything on this side of that line. And then I'm going to show you another way of looking at this as well. Okay, let's graph the other equation. This one I'll graph in red. So here I have 2x plus y is equal to negative 1. If I wanted to, I could plug in a couple of points. If I put in x is equal to 0, I get y is equal to negative 1. So that's what's on my line. And then if I wanted to, if I put y is equal to 0, I get x is equal to a negative 1/2. It almost goes right here. So it's about there. Put in y is 0, x is equal to a negative 1/2. So those 2 points are on my line. But notice it's not equal to. Since it's not equal to, I can't use a solid line. What I have to do is use a dashed line. So over here, I'm going to be using a dashed line. Why? Because the inequality says it's not equal to. Equal to is a solution that's on the line. That is not on the line, so I don't use it. Now I have determined, do I shade that side or that side, above the line or beneath the line? I could use the same test point over here. Put in 0. Is 0 greater than negative 1? Yes, it is. 0 is greater than negative 1, so I shade this side of the line. And since this is a system of equations, I want to find out what X and Y values satisfy both equations simultaneously. That means, where do I have both red and blue on the graph? And you can kind of see it's right here. Now put this as a dashed line. All the way down here it's dashed. And I keep going down here. And then here it's a solid line. And then everything here in between. So that, the green area, is my solution region. So any point that lies in that region will work in both of those. You can just validate that if you'd like. You know, I could pick a point over here. Say this point over here is, 2, 1. Does that work? And I could pick another point over here. Make this 1, 2, 3, comma, -1, 3, and check them out. Put in 2, 1. 2 subtracting 1 is 1. That's less than 3. 4 plus 1 is 5, which is definitely greater than -1. Okay, let's try this one over here. X is -1. So -1 and -3, that gives me a -4, definitely less than 3. And X is negative, so I get -2, Y is 3, so -2 plus 3, 1 is definitely greater than -1. So I can see it works. This is my solution. Everything that's shaded in green. It's critical that this line has to be dashed and this line has to be solid. Because this point over here works, 3, 0. It'll work in, both of them. Because if I put 3 here, I get 3 is not less than 3, it's equal to 3. So that's an okay point. But this point over here will not work. If I put in X is equal to 0 and Y is equal to -1, I get -1 is greater than -1. It's not greater than -1, it's equal to. So that point is not on the line. That's why this line here has to be dashed. And then it turns into a solid. Hopefully that subtle little point makes sense. And that's one way of doing it with test points. Let's take a look at another system of equations that may not be set up or drawn like this, and see how you get essentially the same sort of answer. I think it's best to see several examples, and then you start seeing patterns that come from that. And I'm going to do one more that is very typical, because this is the beginning of an optimization routine, that when you're solving these things, you get these optimizations and something called linear programming. Some of you may have heard of it before, others may have not. It's something that's very, very popular in business and business courses and economics and things like that. Here's another example. So let's say I have it written this way. Y is less than 3x subtracting 4, and y is greater than or equal to a -2x plus 3. Now these are just solved for y. So I can graph these accordingly. So let me set up my xy coordinate system. And start graphing those. Okay, so I go right over here to when x is 0, y is -1, 2, 3, 4. So that's the point on it. I could use the slope and just go up 3, 1, 2, 3, and then over 1. That's another point. I could go up 1, 2, 3, and over 1 again. There's another point. This is not equal to. So when I draw this line, it has to be a dashed line. And that is that line over here, y is equal to 3x minus 4. It's dashed because I don't have inequalities. My solution does not lie on that line. Now, I could either pick a test point or do this. Notice what this says. This says y is less than that value. So that means y is beneath that. When it's less than, it's beneath it. So I actually shade beneath it. The test point would also work here as well. If I put in 0, 0, I get 0 is less than -4. Doesn't work, shade the opposite side. But when I have it solved for y and the inequalities there, I can use it. It's a lot easier than the test point. If it's less than, it's beneath the line. If it's greater than, it's above the line. Okay, so that's my solution region for the first linear inequality in two variables. Now let's put the second one in there. So here I go for my y-intercept of 3, 1, 2, 3. And then I have a slope of -2, so go down 2 over 1, down 2 more over 1. So it looks something like that, but I have an equals there. So that means this is a solid line. And that's the line y is equal to -2x plus 3. And this says y is greater than that. That means it's above it. It's everything above that line. The test point would also work. Pick the origin. Now, the test point doesn't always work. If your line falls on the origin, you might have to pick a different point. But, you know, the origin as a test point works in a lot of the different problems. Meaning if I put 0 in here, I get 0 is greater than or equal to 3. No, 0 doesn't work. It's the opposite side. Now I look where I have both a blue and a red region. So over here, I have this dashed line over here. So that's not a solution if it's on the line. Then I hit this line, and I come down here with a solid, and then all this stuff in between. And you get your answer very simply like that. So that's, you know, an approach for doing this. In need of more ink and my black marker, so let me get that while I'm here. So that's how you solve it. Now, sometimes there's also two more, if you will, equations. Let me show you an example of that after I fill up my marker here. So now let's take a look at this example. Now I'll show you how it all plays out on Desmos. Desmos is a nice little feature that does that too, as well as your graphing calculators. You can take a look at those. If I have time, I'll show that. So let's do one other system over here. Here's my third example. I'll do the y, and I'll do, you know, less than a minus x plus 4, and y is greater than a x with 2x minus 1. And then I might have these two other equations. I might say x is greater than or equal to 0. And y is greater than or equal to 0. Taken together, what these two equations tell me, these just tell me my solution is in quadrant 1. Because if I look at everything over here, and if I were to color in over here, x greater than 0, I mean y greater than 0, and x greater than 0, it overlaps in quadrant 1. So when you have these, you see those a lot. Why is that? Because in the real world, most quantities that we're solving for are positive quantities. A lot of times you do inequalities when you're in manufacturing or you're in shipping and you have some constraints. The things you're selling, you're going to get paid for. Nobody's going to be giving, you know, you're not going to be giving money away, so your profits will not go out. Or you're not going to ship -10 of an item. It's not going to happen. So this is, in the real world, typically everything is in quadrant 1. In math, we can apply certain things to negative quantities, even though in the real world, it may be nonsensical to say, I'm going to ship you, you know, -10 computers. And it makes no sense. But that's where you have it. So when you see that, that just means everything's in quadrant 1. Okay, so let's do the same thing we were just doing with this now. So what I want you to do is set that up. Graph those two equations, inequalities, and shade them appropriately. So I'll let you try that now and see how well you can do on that. I need to add another blue cartridge. So try that. So it's good for you to try it instead of having me do all the well, it doesn't work. Okay, let's go graph this up and see how it looks. So I'll do the top one in blue, and I have my, I'll do this in black so I get my tick marks over here. Okay. So I go to 4, 1, 2, 3, 4, and a slope of -1, 1, 2, 3, 4. It's over here. It's in strictly less than, so over here it is a dashed line. And over here it says y is less than that line. So less than means it's underneath. That shade underneath. Okay. Then I could move to the second inequality there and go down here at -1, and I have a slope of 2 up 2 over 1. Again, it's in this case, so it's this way. It's a dashed line. That's y is equal to 2x minus 1. That's not part of my solution region because it's not equal to. This says y is greater than, so it's above that. Okay, now let's see if we can figure out our solutions over here. This tells me that I have to be in quadrant 1. So what does my solution region look like? Well, it looks like this over here. This is, since it's equal to here, I can shade in that portion of the x-axis. I can also shade in this portion of the y-axis. This is the dashed line, because that's part of that blue solution. And here's my, if you will, my y, which is also a dashed line. And everything in this little sliver of a region, that's my solution region for what I've done now. So anything over here, that means y would not be greater than 0. Anything back there, x would not be greater than 0. That's why I can't shade it in. That's why none of this gets shaded in, because it says x has to be positive. Does everyone see that? So there's my actual solution region. Now you can actually see this using Desmos here. So let me kind of go on and show you that as well. It's another thing that Desmos has, all these capabilities. And I think it can be very, very helpful. Let's just exit, exit, and come over here and put the equality. So y is, less than minus x plus 4. And the other one, see how it colors in, y is, and use a dashed line there as well. You can kind of see that. Greater than 2x minus 1. And if I wanted to, I could include x is, greater than or equal to 0, and y is greater than or equal to 0. A little bit harder to see, but the only thing that everything is saying is this region over here. I usually don't do these because I know what it is. It's harder to see. Excuse me. Well, sometimes I'll just shut those off because you can actually come over here and, get rid of the color. Okay, let me just do that. I can just do this. That's right. Turn it off, toggle it off, toggle it off. And I can see where the purple and the black overlap in quadrant 1. So there's my little line here, dash, dash. That should be solid. Has to be in the first quadrant. And notice, because they're less than or greater than, there is no solid line. If I just simply change that to less than or equal to, then you see it becomes a solid line. So hopefully you see now why it's dashed or solid over here. But that's my solution over here. And I can change the colors to make it look a little bit more interesting if I wanted to. So all the things we've done in this section would follow that same process there. Now you can do it on your, I haven't done it too often on your TI calculator. You can try that. If you have any questions, I'll go over that next time. But this is easy enough to do on your own. This is why you may want to, either on the test or something, have some basic graph paper that you can use. You can probably just print it out instead of having to buy a whole big, packet of it. You can just go online and just print out a couple of sheets of graphed paper there and just kind of do what you need to do. And when we get to a test to solve some of these, you will have to do some graphing and show me the shaded regions. Any questions? Anyone think this is relatively easy? You need to know how to graph your lines. So that's a prerequisite really for this course. It's in your basic algebra and intermediate algebra, how to graph simple linear equations in two variables. And now we're using that, and then we're just kind of making an inequality. We're shading certain regions. Now we can't write this algebraically. You can't write something that's algebraic like this. You have to show it visually. And that's the problem. Now the interesting thing is when you want to optimize this shows you all the solutions. Usually you want to find all the solutions and you want to find the unique solution that'll either maybe minimize something or maximize something. Amazingly, it turns out, according to linear programming, that the solutions always occur at a vertex. So as long as you find those intersections, you can figure out your optimal solution. That was actually discovered by a gentleman by the name of George Dantzig. It was amazing. He was in graduate school, and he got to his graduate course in mathematics a little bit late. He came in late for whatever reason, and there were problems up on the board, so he copied them down and just sat through the lecture, and he thought they were homework assignments. And then, a couple of weeks later, he went into the professor, all apologetic. I'm sorry, I couldn't get all the solutions, but I got this one. I'm sorry the homework's late, but I apologize. And the professor turned around and looked at them. Well, these were famous unsolved problems in mathematics, and apparently you just solved one of them. So it's the power of positive thinking. If you think it's something that's just a homework assignment and you should be able to solve, you can solve it. If someone tells you in advance that it's an unsolved problem, you're not going to approach it that way. But that was kind of the genius he was. He's the father of linear programming and created all that. But when you have a mind like that, so I guess it pays to be late to class once in a while, but not always, not all the time. But I always love that story. Any other questions? Anything else here? Because that's all we have for today. It's just a short lecture. These sort of problems, I gave you the three generic types of example. The critical things, if it's just a less than or a greater than, dashed lines. If these occur, it's just in quadrant 1. where x and y are greater than 0. Now, if you have it solved for y, then it's easier to do. If it's less than, it's beneath the line you've drawn. If it's greater than, it's above the line you've drawn. If it's not written in this way, you can either solve it for y, or you could just use a test point. Now, sometimes you get the line like y is equal to negative x, so the line actually falls right on the origin, so you can't use the origin. But you can use any other point in the xy plane as a test point. And the test point methodology is if it solves that inequality, then all points on that side of the line will solve that inequality. And that's the logic behind that. Okay, so let me kind of give you some homework for this. It's not too bad. And that's our systems of equations and inequalities. Now, I might mention, if we had time, if we don't, we could also solve nonlinear systems of equations and inequalities just by graphing parabolas and circles and then shading regions appropriately. We're not going to do that, but you can see where you could extend that general idea from linear to nonlinear. As long as you know how to graph the various functions and or relations, you can quickly and easily show. Just like we solved the nonlinear system of equations, you can do the same thing to solve a nonlinear system of inequalities. Same sort of thing.